A computer does not see the light in a photograph or hear the tone of a human voice, but at the physical hardware level, everything is reduced to a rapid, continuous stream of binary electrical signals. The real world is full of nuance and context, details that remain completely invisible to a processor when they arrive as raw, unorganized data. To bridge this gap, we use a branch of mathematics that turns abstract concepts into physical structures: linear algebra. Look at this user profile. By recording specific traits as a vertical array of numbers, we create a vector. This vector allows us to plot a person's entire purchase history as a single, precise point on a coordinate grid. Mapping data in this way transforms information into a physical location within a navigable mathematical universe. This mapping becomes a massive logistical challenge when an algorithm has to process millions of these data coordinates simultaneously. We manage this scale by grouping vectors into matrices, organizational grids that allow the computer to perform calculations on entire datasets at once. Machine learning happens by mathematically stretching or rotating this matrix. These transformations align disparate data points onto a shared axis, making it possible for an algorithm to compare items that originally seemed unrelated. A matrix isn't a static storage table. It is the set of mathematical instructions that defines how the data's environment should be manipulated. Once that environment is established, the machine can begin to ask questions, starting with which pieces of data are most alike. This diagram illustrates Euclidean distance. It is the direct way a machine measures similarity, calculating the literal straight-line distance between two coordinates. When a direct path is too computationally expensive, the machine uses Manhattan distance. This measures the gap by following the grid's 90-degree angles, much like a car navigating city blocks. These physical measurements allow the machine to determine if two items share a similar scale or magnitude. But distance can be misleading. A long, detailed article and a short summary will sit very far apart simply because one contains more data. Using a dot product to calculate cosine similarity, the machine measures the angle between vectors, seeing they point in the same conceptual direction. To see raw shared information, Jacquard similarity calculates the intersecting area between two sets, highlighting their exact overlap. By focusing on angles and overlaps, the machine identifies thematic relationships, while ignoring how large or small the individual files are. Modern data is often too complex to visualize. An image or sentence can have thousands of dimensions, creating a space too dense for immediate calculation. Using projections and orthogonality, the machine casts a lower dimensional projection, creating a simplified shadow of a complex cloud onto a flat surface. This projection preserves the most important spatial relationships between points, while stripping away dimensions that don't contribute to the overall pattern. Simplifying the geometry in this way is what allows modern hardware to process massive datasets in a fraction of a second. Curious, but how does the machine know which angle provides the most accurate shadow? Through singular value decomposition, or SVD, the algorithm calculates eigenvectors. These are axes that slice through the data where it is most spread out, capturing the directions of maximum variation. Because SVD identifies where the data changes the most, it allows the machine to ignore the noise of stagnant data and focus on the few specific features that actually influence a prediction. When an algorithm recommends a movie or translates a language, it isn't thinking in the way we do. It has no intuition or personal preference. It is simply moving vectors through a matrix until it finds the coordinate that is mathematically closest to the target. Linear algebra allows us to map the complexity of the human experience into a geometric language, giving machines a structured way to calculate the world around them.